1 minute ago, somewhere in a physics lab, a particle did something that should be impossible. It did not just sit still, and it did not just move forward the way every particle in history has moved forward. It went backward, not metaphorically, not in a simulation. Scientists have now built real control systems that make quantum particles behave as though time itself is running in reverse. And the implications are so strange that even the physicists who did it are being careful about how they explain it. This is not one isolated headline chasing clicks. It is the latest chapter in a long research tradition, stretching from a landmark 2019 experiment on an IBM quantum computer to a brand new 2026 study out of Los Alamos National Laboratory that has physicists rereading their textbooks on entropy. Teams in Vienna, Chicago, and now New Mexico have each found different ways to make the impossible measurable, and everyone insists this is real, reproducible science, not a magic trick. For over a century, one of the most stubborn rules in physics has been the arrow of time. Eggs crack and never uncrack. Heat flows from hot to cold and never the other way around on its own. This is entropy, the tendency of disorder to increase, and it is one of the only laws in physics that cares about direction at all. Almost every other equation governing the universe works the same whether you run it forward or backward. Only entropy insists time moves one way, which is why you remember yesterday but not tomorrow. The second law of thermodynamics has survived every serious challenge thrown at it since the 19th century. Einstein once described thermodynamics as the only physical theory he believed would never be overturned, a remarkable statement given how many classical assumptions he went on to dismantle. That reputation is why any research claiming to bend the arrow of time draws heavy scrutiny before it's taken seriously, and why the growing evidence behind quantum time reversal has become such a big deal. Quantum mechanics complicates this picture. At the tiniest scales, the fundamental equations describing particles do not actually forbid time from running backward. The forward-only arrow we experience in daily life emerges from the statistics of huge numbers of particles interacting messily, not from any hard rule in the underlying physics. A gap that a new wave of research has started prying open. The most talked about result comes from a team at Los Alamos National Laboratory led by physicist Luis Pedro Garcia Pintos, published in February 2026 in Physical Review X. The team designed quantum control protocols, engineered combinations of measurements, feedback, and tuned fields that reshape how a quantum system's arrow of time behaves. Using a control Hamiltonian, a mathematical blueprint for a sequence of pulses and fields, researchers found they could cancel out, strengthen, or even flip the natural disturbances caused by quantum measurement, producing trajectories that looked stretched, blurred, or fully inverted compared to normal. The team generated time-reversed stochastic trajectories, random paths engineered to look more consistent, with time flowing backward than forward, building directly on Maxwell's demon. The 19th century thought experiment where a hypothetical tiny observer sorts hot and cold particles in a way that seems to violate the law that disorder should always increase. The Los Alamos team essentially built a real working version of that idea in a lab setting. This isn't the first time researchers have pulled this off. In 2025, a team at the Austrian Academy of Sciences and University of Vienna, led by physicists Miguel Navasquez and Philip Walther, used single photons in a device called a quantum switch. They sent a photon through a crystal, let it evolve, then used the switch to undo its own evolution without ever needing to fully observe or understand what was happening inside the system. The photon rewound itself with more than 95% fidelity. What made this remarkable is that it worked without detailed prior knowledge of the system's internal dynamics, the major roadblock in earlier attempts. It worked for any two-level quantum system, a qubit, ran in real time, and the researchers even demonstrated they could fast-forward a quantum state as well as rewind it, with real applications for correcting errors inside quantum processors. To understand how unusual this all is, go back to the experiment that started this line of research, a 2019 study out of Argonne National Laboratory, led by senior scientist Valery Vinokour with researchers from the Moscow Institute of Physics and Technology. They built an algorithm on IBM's public quantum computer to simulate a particle scattering off a two-level quantum system, like a billiard ball struck by a cue, letting the simulated particle evolve from a localized state into a scattered one before running the algorithm to throw the process into reverse. The particle went back. On a 2-qubit version, it returned to its original state 85% of the time. Scaled up to 3 qubits, that rate dropped to roughly 49%, showing that reversibility gets dramatically harder as the number of interacting particles grows. Vinokour said the team had done what was considered impossible, giving physicists their first real experimental foothold on how the second law behaves in the quantum world. The Argonne team also introduced the Loschmidt echo, named after 19th century physicist Joseph Loschmidt, a diagnostic tool measuring how reversible a quantum process is. Run a system forward, flip the sign of the interactions driving it, then see whether it retraces its steps. The closer it returns to its original state, the higher the fidelity. This technique has since found practical use beyond pure physics curiosity, including in methods that optimize how qubits get assigned on Google's superconducting hardware. The Maxwell's Demon connection explains why this research carries so much weight. Maxwell proposed his demon in 1867 as a challenge to the second law, a tiny gatekeeper sorting fast, hot molecules from slow, cold ones without doing obvious work. For over a century, this was just a thought experiment, since nobody could build a device that sorted disorder into order without paying an energy cost elsewhere. It took physicists most of a century to resolve why the demon doesn't actually violate the second law. Physicist Rolf Landauer showed in the 1960s that the demon's sorting only appears free because it ignores the entropy cost of erasing the demon's memory. Once you account for that, the books balance again. This principle, Landauer's bound, remains one of the deepest links between physics and computer science. Modern quantum control techniques, including the Los Alamos study, have turned Maxwell's thought experiment into something built from real pulses, measurements, and feedback loops, effectively probing exactly where that boundary sits. That's where this stops being just a curiosity and starts having real stakes. Quantum computers are fragile, threatened by decoherence, where delicate quantum information leaks into the environment and gets lost. If researchers can reliably rewind a system to an earlier, cleaner state, they could undo damage from decoherence before it ruins a calculation. Physicist Andrea Rocco, not involved in the Los Alamos study, said reversing time at the quantum level could help stem exactly this kind of information loss. Decoherence is the single biggest reason quantum computers are so much harder to build than classical ones. A classical bit is robust against heat, vibration, or stray noise, while a qubit is sensitive to any unwanted interaction. Once a qubit's state leaks into the environment, there's no known way to gather it back up, which is why quantum time reversal is so tantalizing. Companies building today's quantum computers already spend enormous effort managing decoherence through brute force, isolating qubits in superconducting circuits near absolute zero, or trapping ions in shielded vacuum chambers. These work to a point, but treat decoherence as an enemy to wall off rather than reverse. A reliable, time reversal-based toolkit would reclaim leaked information after the fact, instead of just preventing the leak. The Los Alamos team's next phase will test their control techniques directly on superconducting qubits, the same general hardware Argonne used years earlier, moving from a proof of concept on a couple of qubits toward a fully engineered framework for far more complex systems. Nobody has built a time machine. Nobody is sending information into the past or creating paradoxes. What these experiments demonstrate is narrower and more remarkable because it's real. Physicists engineered the statistical behavior of small quantum systems, so their evolution looks locally suppressed, stretched, or inverted, using measurement and feedback rather than breaking any law of physics. As one writer covering the Argonne experiment put it, nobody sent anyone back to meet the dinosaurs. The experiment reveals how much creative room exists within the laws of physics, not a loophole in them. This also explains why entropy behaves differently depending on scale. A single qubit involves so few particles that the odds of retracing its exact path backward are reasonably favorable with careful engineering. A shattered teacup involves something like a septillion atoms, all needing to simultaneously reverse in perfect coordination. A scenario so improbable, physicists treat it as impossible, which is why the 3-qubit Argonne experiment saw its success rate drop so sharply, and why nobody expects quantum time reversal to scale to anything visible to the naked eye. A separate but related line of research, published in Physical Review Letters in April 2026, explored quantum signatures of proper time in optical ion clocks, treating time itself as a quantum variable rather than a fixed backdrop. This sits at the intersection of quantum mechanics and Einstein's relativity, two hugely successful theories, never fully reconciled. Researchers propose that a trapped ion in quantum superposition could, in principle, experience two slightly different rates of elapsed time simultaneously. Nobody has run this exact experiment yet, but the theoretical groundwork gives physicists a concrete, testable target. This broader program sits within quantum thermodynamics, a young subfield treating heat, work, and entropy as probabilistic quantities. The Los Alamos study was supported jointly by the DOE's Office of Science, its Advanced Scientific Computing Research Program, the lab's Beyond Moore's Law Project, and the National Science Foundation, signaling that government agencies see this as relevant to the national push toward practical quantum computing. So what actually changes in the near term? The most realistic application is quantum error correction, the challenge standing between today's fragile quantum computers and reliable ones. Current error correction spreads a single piece of quantum information redundantly across many physical qubits, so the system can detect and reconstruct a corrupted value, similar to how a hard drive uses checksums. But it's expensive, needing dozens or hundreds of physical qubits to protect one usable unit of information. A genuine time reversal-based method would instead rewind a corrupted state back toward its clean version, potentially cutting the redundant hardware needed for fault tolerance. Researchers stress this remains early and unproven, but the potential payoff is large enough that multiple groups worldwide are chasing it. There's a deeper payoff too. Every time researchers find a real way to manipulate the arrow of time, even narrowly, it chips away at our understanding of one of reality's most basic features. Philosophers have taken notice too. If time's arrow is an emergent statistical pattern rather than a fundamental law that raises old questions about how solid our intuitions about cause and effect really are, some physicists now describe entropy and time's passage less as fixed features of the universe and more as a large-scale illusion built from trillions of small-scale quantum processes that individually don't care which direction they run. This research also sits inside the larger global race to build powerful, reliable quantum computers. Every major country and company investing in the field, from the US and China to Google and IBM, is chasing the same prize: a machine that can solve problems no classical computer can, from simulating drugs to breaking encryption. Every obstacle traces back to the fragility of quantum information once it interacts with anything outside tightly. Controlled conditions and time reversal research is one more serious attempt at solving that problem from a different angle. The original 2019 Argonne experiment is still being cited and built upon 7 years later, a rare kind of longevity that signals this direction has real staying power. None of this means quantum time machines are coming anytime soon, and if anyone tells you scientists are building a way to travel into the past, that isn't what this research claims. What it does mean is that the boundary between science fiction and laboratory reality just moved a little further, and researchers are